And our next talk is at two-put sidechain assisted chosen ciphertext attacks using valid ciphertext on HQC KEM. And the speaker is Cyan. Stage is yours, Cyan.
Thank you very much for the introduction. So I'm here to present a paper on the side channel assisted chosen ciphertext attacks using valid ciphertext on HQC KEM. This has been a collaborative work, and I think let's start. So this is the outline of the presentation. I'll just go through a brief introduction on HQC and then explain the operations that we target on our side channel analysis. And then we also show that shuffled implementations are not safe from our side channel attacks and provide the concluding remarks along the way. So a brief introduction to KEMs. Alice and Bob trying to communicate with each other. Alice generates a key, sends the public key over to Bob. Bob encapsulates it and then sends it back to Alice, who actually decapsulates it. So this is in a static key setting. Alice actually reuses the key pair for multiple KEM instances. So this is the main target of our work, the decapsulation procedure, where manipulation of the same secret key in multiple executions has been done. To give a brief introduction to HQC and its structure, so it's based on Hamming quasi-cyclical and decoding of syndrome decoding. So the authors actually propose in CPA secure encryption and decryption module, where they generate the parity check matrix and sample two vectors x and y as the secrets and generate the public key along the way using the equation in line 4, x plus hy, and then return the public key and secret key. The encryption procedure is also pretty standard, where U and V is actually calculated as the ciphertext based on some pseudo-random samples that are taken from using a particular seed. And then the decryption procedure follows, which is actually also a standard. And we can see that this is the main highlight of our work. So just to go over the encoding process for HQC, HQC actually uses repeated Reed-Muller and Reed-Solomon codes. First, if the message that's been supplied has k bits, then it's encoded using a Reed-Solomon code, and then each 8 bits of the Reed-Solomon code is passed through a Reed-Muller decoder, which again converts it to 128 bits, and then we have N1 and N2 bits, N1 cross N2 bits of Reed-Solomon Reed-Muller codes. So just to look at the decoding process for HQC, which we actually target. So the first step is expand and sum. So this removes the multiplicity of the 128 M code words, where M is actually the multiplicity that's targeted. It actually sums up 0 to M minus bits for each code word in 128 blocks and comes up with an integer. Next, the Hadamard transform. This is actually done in to calculate the likelihood that message associated with the corrupted code word is index, or it's the binary representation of index plus 128. Then comes the find pix, which actually is the operation that finds the position of the highest absolute value. So we target these two operations, expand and sum, and find pix on our attack, and let's get to it. So this is the C implementation that's available in PQM4 as a reference implementation for HQC. So we have used that in our attack. So if you see step 1, there is a bit manipulation going on, where there is a shift operation applied that extracts the bit.
Could you speak a little bit louder, please?
Sure.
Thank you.
So for each byte, the source code word is actually calculated and extracted into the DEST variable. Uh, and in step 2, it is done for actually the M-1 code words. So what we do is for detecting the leakage, we use code words and fix the first bit as 0 and first bit as 1 in 2 sets using 10,000 separate code words. And we perform decapsulation of the ciphertexts. And as the TVLA analysis shows here, there is significant leakage for several of the bits. So these are the leakages that have been exploited in our attack. So we actually build a template for recovering the corrupted code works. Basically, we reduce the trace set by determining an empirically determined threshold and calculating some reduced points. And then we use the mean and variance of each reduced trace set, which becomes our template. And this is, we use Gaussian estimator to build the maximum likelihood of each bit to be 0 or 1 for the code word. And hence, by this process, we actually recover the entire corrupted code words C. So yeah, there are errors while recovering the code word. And as seen in figure 1, I mean, the error actually reaches around a little over 20%, while in figure 2 it's also 20%. But our experimental results and averages indicate that the error rate of retrieving the correct code word is 14%. So for key recovery algorithm, we actually generate eta number of valid ciphertext using our own constraints, using the values R2, R1E, which are the pseudo-random samples I have told about. So after that, we get an approximate eta number of linear equations, which we actually solve. Basically, HQC decoding relies on the sparsity of the products X R R2 and Y R1 and the sum X R2 and Y R1. So the consequence of this is that the vector of the code word and the encoded message, the difference between them contains many ones, which aligns with the circular shifts of R2 and R1. So this is actually dictated by the non-null entries of X and Y. So after calculating a high number of traces, we can compute the likelihood of an index being 1 in X or Y respectively. The likelihood is actually calculated by measuring the similarity between the corrupted code word, the difference between the encoded message and the corrupted code word, and R2 for X and R1 for Y. So our key recovery algorithm iteratively fixes zeros in X and Y based on their likelihood vectors and solves for the remaining n unknown bits using the binary key equation S equals to X plus HY, which we actually use to derive the public key. So correctly guessed zeros ensure successful key recovery. So to present the results, the attack achieves full key recovery with significantly fewer traces compared to prior works, requiring only 2 traces for an error rate of 14% and handling rates up to 35% with equivalent to 25 traces. Previous works actually had 10,000 to 20,000 traces in earlier methods. So this is a significant improvement over that. So next, we move forward to the fine peaks algorithm. We exploit the vulnerability in the mask variable that is being manipulated to actually calculate the position. So the mask variable actually switches between the value 0 and 15 depending on whether the current value absolute is greater than the previous peak value or not. So by tracking the mask variable, we actually find a heavy leakage because it's a high leakage of around 16 bits. So, and we build a test-based template for the mask during the 128 iterations for differentiation. And as we can see that the traces show very significant leakage for fine picks than for expand and sum. So this side channel analysis leverages failures in the RM decoding process, and it's represented by a vector D to reduce information about the weight of error blocks, which actually correlate with the non-null entries of X and Y. So using sufficient SEO observations, we compute vectors W1 and W2 to approximate the weights of X and Y's possible slices and revealing their distributions and enabling key recovery with very high precision. So actually we noticed one thing that even a small error probability change will actually slide up the number of traces from 200,000 to over 1 million. So our conclusion is that the fine pix version, the function fine pix is very susceptible to noise. So it actually requires an average of 188,333 traces under perfect conditions, and expand and sum actually recovers the full key fewer than 100 traces. Coming to attacking shuffled implementations, so we have considered two shuffled implementations. One is intra-code word shuffling and inter-code word shuffling. So there is leakage of individual bits, but the attacker cannot directly infer the bit positions without knowing the random shuffling order. So our side channel attack was still able to recover the individual bits, but the error rate was pretty high with 25%, and it does add a significant difficulty. So as you can see from this diagram, where we required only 2 traces to recover the key for expand and sum without shuffling, it actually took us 681 traces in the 95% quantile to get the full key. So the attacker uses side channel analysis to actually approximate the Hamming weights of the noisy RM code words. It actually calculates the difference between the RM code word after encoding and the approximate Hamming weight of the noisy Reed-Muller code word. After a large number of side channel traces for the description, the process actually builds likelihood vectors similar to that used in non-shuffled versions. The attack requires an average of 681 side channel analysis traces to successfully recover the full key. So this shows that the power of error-tolerant recovery algorithms to deal with the noisy SCA information, and it highlights the problem of bitwise leakage between when protected with shuffling. So the proposed key recovery method can be extended to handle intercode word shuffling as well. So in this case, the Reed-Muller blocks are shuffled among themselves. The attack can still recover the key by using the Hamming weight of the full noisy code word. And we achieve a key recovery with around 64,000 traces. Now for a shuffled implementation of fine picks, it's almost the same thing. So a random permutation is generated for the main loop, and we exploit leakage of one information invariant to shuffling. It's actually the number of unique values. We show that this is correlated to the number of peak changes that are detectable with side channel attacks, which turns out to be related to the weight of the RM blocks. So we use the same key recovery algorithm that we used previously for a non-shuffled explanation, and but we consider that many ciphertexts need to be used right now. So previously we actually had 200,000 traces, but for this we actually required 21 million ciphertexts. So just to provide my concluding remarks, the decapsulation failure check countermeasure will not work with our attack in place because the leakages from expand and sum and find peak operations can be exploited to recover the secret key when using valid ciphertexts. The attack actually exploits leakages from both expand and sum and find peaks. So these leakages allow for 100% key recovery even with significant noise in the side channel, even with large number of traces, but it still recovers with 100% key recovery. The effect of shuffling is not that large because even if it is slowing down the rate of analysis, it still is able to retrieve the key. So for expand and sum, we have the key within less than 4,000 traces, but for find peaks, actually it grows 100 times more. So the future direction or the only countermeasure that we can think of right now is masking and shuffling both to be implemented. And there's definitely a very high need of implementing an efficient masking scheme for HQC as it has been currently standardized by NIST. Okay, thank you.
Thank you for the talk. Are there any questions from the audience? Okay, then I'll start. So you measure your number of traces per bit classification rate or bit success probability, right? Can you somehow relate this to SNR, to signal to noise ratio?
No, we actually checked that, but I don't think so there's a relation for that.
Okay.
Yeah.
Anyone else? Okay. Then maybe another question. So instead of countermeasures, could you implement the routines differently so that maybe they don't leak the bit as strongly? Exactly. Because I assume, given the high success rate you have for recovering a bit, that probably there's less switching, so maybe you can somehow implement them differently. Would that help?
Yeah, I definitely think there's scope in that. I mean, going for a different approach towards the decoding itself might help. So maybe approaches towards a maximum likelihood decoding for the Reed-Muller decoding process might be a little easier to mask as well. Yeah, so we are actively working on that. Yeah.
Okay. Thank you. Then let's thank the speaker again if there are no questions. Okay.
Thank you.